Okay, so today I want to discuss one of the very first things you talk about when you take a course in partial differential equations. Uh, you want to understand if a partial differential equation is linear. So the most some very important things are figuring out how to show that a PDE is linear, because if we can find out whether or not a partial differential equation is linear or not, we can take advantage of many properties from linear algebra, such as the superposition principle. Superposition principle, which just basically says that you have, let's say, one solution, u1, you can add to it another solution, u2, and u1 is a solution, u2 is a solution, and u1 plus u2 is also a solution. This is very desirable property about linear partial differential equations, amongst the many other things that being linear brings about. So let's get to the idea, basically. So we do know that a partial differential equation is an equation involving partial derivatives. Hence the partial. Whereas a regular ordinary equation, commonly known as ODE, ordinary differential equation, contains ordinary derivatives. This contains partial derivatives. So basically, we have to consider a partial differential equation as a function, we can call it big F, of many little independent variables, x, t, infinitely many more. But let's just say we have a finite amount. In this case, we can say a partial differential equation is a function that is of the form x, t, u of x, t, u partial x of x, t, and u partial y of x, t. And we can say this is all equal to 0. So a partial differential equation is an equation of this form right here, where you have all these terms on one side that come from one main function u, and u, that function right there, is the solution to this partial differential equation. If we could just find out what u is, u of xt is the solution. Is a solution that we're looking for this specific partial differential equation, which, by the way, is degree 1. F is first order. It's a first order PDE because u of x and u of y are the first. They are the first partial derivatives. Partials. So if it would have been like u double x, then that would have been a second order PDE. So that's those properties. And we usually discuss these properties because by properties I mean we have order, and what is this? Yeah, leave me alone. So we have order as a property that we're interested in, and we also have linearity that we're interested in. These are properties that classify partial differential equations, and when we classify them into groups, we can therefore use similar techniques to solve those equations that fall into a certain group, or we can just in general find out interesting things about those equations and just use them, apply those things that we know about that group to those equations in that group. Another thing we have to understand is whether a partial differential equation such as this is equal to some term g at the end or 0. Let's say it's equal to some term g or some more terms. This is equal to some stuff here. We can say that this PDE is not homogeneous. In this case, it's not homogeneous because it's got this term here. Let's say, for instance, though, that this was just all completely, let's just say this was 0. In this case, it's called homogeneous because it's set equal to 0. So we have linear, nonlinear. So a PDE could be linear, nonlinear, homogeneous, non-homogeneous. Same thing with nonlinear, homogeneous, non-homogeneous. We have order, so it'd be like first order, second order, and so on. And same with this. These nonlinears can be multiple orders. So this is just a classification of small details of a PDE. But now let's actually get to the idea of how to show that a PDE is linear. Okay, so the main things that we want to think about. So let's consider what it means for something to be linear in general. And this comes from the idea of a linear operator. In the study of linear algebra, you say that a linear operator has to follow, has to satisfy two properties in general for it to be linear. And we say that a PDE, so this is important right here, a PDE is called linear if for two functions u and v, for two functions u and v and some scalar c, we get that some operator acting on the function u plus v is equal to that same operator acting on the function u plus that same operator acting on the function v. And the same operator, or some operator, acting on the function c times u, so there's a scalar times the function, is equal to the scalar coming out times the operator acting on the function u. If we can show that these two properties hold, then we have shown that a partial differential equation is linear. So let's get some examples. Let's think about this right here. I have a function. We can say that actually I have a PDE right here. We want to verify. So let me go ahead and write this so you guys can see as an example. So example. Okay. Determine if the following are linear or not. Determine whether the following are linear or not. So let's say the first one, we have partial t u partial t minus I partial u x x. This equals to 0. So we want to verify whether this is linear or not. So we have some function u, they're taking its partial with respect to t minus I, where I is equal to the square root of -1. It's the imaginary unit. So we're going to work with that. And we want to verify this. So we start off by identifying the operator that would create this scenario right here. And I could say that an operator would be something of the form L of f is equal to, and notice how this is the partial with respect to t of some function. So I'll just say that this is dt partial d respect to t of the function f, whatever that function may be, minus I times the second partial derivative of the function with respect to x of the function f. So whatever function f I decide to plug into here, I get that it will be equal to the partial with respect to t of the function f minus I times the second partial derivative with respect to with respect to x of the function f times I. Okay, so I want to show this right here. So this is what I'm going to say. I'm going to say let suppose u and v are functions that we can differentiate twice. And so now consider L, the operator that I have defined right here, the operator acting on the function u plus v. Well, we want to show this. Remember, we have to work with this. So everywhere we see an f here, we're going to plug u and v in. So we have partial with respect to t of u plus v minus I times the second partial derivative with respect to x of the function u plus v. Well, what is this equal to? Well, this is just equal to partial u sub t right there. Partial d dt acting on v will be plus v sub t minus I times uxx, the partial derivative with respect to x squared acting on u, so it would be uxx plus vxx. Now I'm going to go ahead and distribute this negative I into it, and I'm going to rearrange terms. So I get u of t minus I uxx plus v sub t minus I vxx. And now this is where I start to notice that these two terms right here is really just L acting on u plus this term right here is really just L acting on v. And so if you notice, we satisfied the first property, that L of u plus v has to equal to this. Has to equal to L of u plus L of v. Also, consider for some c scalar. So we can say c is an element of the field. We can consider L of cu. Well, it's going to go through the same idea. Cu, we're going to plug, that's our f in here, we're going to plug that into here. So we get second partial derivative with respect to t of cu minus I times the second partial derivative with respect to x of cu. Well, this is equal to cu partial t minus I. The c can come out because we know differential operators are linear. So this c can come out, so it's I times c times u x x. Well, this is the distribution of a scalar between two constants, I mean between two terms. We know we can factor this out. So this is c times u of t minus I u x x, which is really just equal to c times L of u. And therefore, this equals to this, so yes, it is linear. So yes, 1 is linear. It's a linear partial differential equation because its corresponding operator is linear. Okay, now I want to consider another partial differential equation, and I want to consider its linearity or non-linearity. So let's think about this equation now. The next equation I want to work with, I'll call this one number 2. This is equation number 2. And this is u of x plus u times u of t equals 0. So I want to see whether or not this is linear. So once again, consider two functions, u and v. But first, I want to find the corresponding linear operator that would give me this right here. So the linear operator acts on a function and it gives you another function. So basically, I took a function and took its partial derivative with respect to x, so I could say this is dx of some function f, and I'm adding to it the function f times dt of the function f again. This is the partial. This is the linear operator. This is the not linear. I can assume that this is the operator that gives me these two terms right here. So now I want to go ahead and see what I get when I do L of u plus v. Well, L of u plus v will be dx of u plus v plus u plus v d partial t u plus v. So this right here would just be equal to ux plus vx plus these two stay the same, which is u plus v times, and this is the partial derivative with respect to t acting on u, which is u sub t, the partial derivative with respect to t acting on v, which is v sub t. And so now I notice I have a ux, a vx, and I can just distribute these two terms, double distribution, ux plus vx plus, I get a uut, u vt plus u vt, v ut plus v ut plus v vt, v, let me erase that, that's a v vt. Okay, so I want to look at what this is right here actually. What happens when I take I'm trying to get this scenario LU and LV. So if I plug in a U in here and a V in here, if I plug in a U into here, I get partial U time plus, so I get U sub x plus U sub t. So here's my U sub x plus U sub t. Oh, that's right there. Sweet. u sub t. So far I have taken care of this term and this term. Now I'm going to go ahead and think about what happens when I plug in a v. This v, I'm going to plug it into here now, v. So I get v sub x plus v sub t. So v sub x right here, v sub x plus v sub t, which I have right there. So I took care of that. What about these two terms? What is this? This is like extra junk. It just came out of nowhere. So it would have been linear, except this right here makes it not linear. Because we have extra stuff. This would have been nice if it would have just been this and this, because then this would have been L of u and this would have been L of v, but it's not linear because we have this extra random stuff showing up. Okay. I have another example I want to also discuss. Basically, it's another linearity problem. And this one is slightly more involved in the sense that I want to discuss about where it comes from. And this one, I'll call it Laplace. Laplace's equation. Laplace's equation. So, Laplace's equation is a very, very common equation in the study of physics, and just pretty much when you study nature, you will see this equation showing up a lot. And I will write it down so we can look at something. uxx plus utt equals 0. So it is an equation of this form. It is a second order partial differential equation because you have the second partial derivatives. And I kind of want to discuss about, I want to show that it is linear. I want to get to that. I want to show whether it is or it is not linear. I want to get to that. But I kind of want to discuss about where it comes from. I think this is a good way to kind of start talking about operators in general, since we already talked about operators. Let's think about this. This equation is so common that they've actually named an operator after it. It's called the Laplacian operator, and it is usually denoted as u phi. Actually, let me get rid of that right there. It's very ugly. This is the Laplacian acting on some function u, and I'm going to go ahead and call this what it is. It's a Laplacian operator. Laplacian operator. And as far as what the Laplacian operator is, or what it does, really, it is the divergence. It's the divergence of the gradient of some function u. So let's look at this. This is the Laplacian operator acting on a function u, and I'm telling you that the Laplacian operator acting on a function u is really equal to the dot product, which is called the divergence of it's the divergence of the gradient of u. So this is the gradient of u. So this is gradient of u. So now you have all this stuff in front of you. So what does gradient mean? Well, I want to get into the idea of what the gradient is. Here's the basic definition that I could find. Kind of had to tailor it a little bit. Basically, the gradient of a function u of n variables, n independent variables, is equal to the sum, or the linear combination of, actually no, it would be a sum, I equals 1 through n of the partials, partial with respect to u, t t of xi, where I is the index that is ranging from 1 to n, because we have n independent variables on the function u of the in the directions of the unit vectors. So basically it becomes a vector function. You have some function u, you take the gradient of it, and you really end up getting the sum of the partial derivative in the x sub I direction of the function, and it is the sum. So basically, if you have, like, let's say, like, let n equal to 10, so you have like 10 dimensions, and you want to find, or 10 independent variables on the function u. So the gradient of the function u is the sum from I equals 1 to 10 of du dx I e sub I, which is really equal to du dx1 e sub 1 plus du dx2 e sub 2 plus dot 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 plus du dx10 e sub 10. So you're kind of taking the partial with respect to x sub 1 and putting it in the x sub 1 component, and x sub 2 putting it in the x sub 2 component. So this is a vector right here, and I can write that in vector notation as u sub x1, u sub x2, all the way out to u sub x10. So in every component I am putting the corresponding partial derivative in that direction. So this is in the x sub 1 direction. I'm putting the partial derivative of that function into the x sub 1 component. Same thing here, the x sub 2 component, so there it goes in there. So this discussion of Laplace's equation basically brings birth to all this rich math. This is a partial differential equation. Like I said, we're going to show that it is linear, but I want to kind of show Laplace's equation. So I want to get to this Laplacian operator. Notice, I didn't give you a direct formula for what the Laplacian operator is. All I'm telling you is that the Laplacian operator is the fancy divergence of the gradient, which is really not a big deal. It's really just the gradient dot product of a gradient. So it is the divergence of the gradient of some function u. So suppose I want to kind of derive this equation right here. I want to derive that. So suppose we want to find the Laplacian operator of, so suppose we have a function, we have u of x, y, and we want to see the Laplacian operator of acting on that. So basically, suppose we have this. What is the Laplacian of u? What is the Laplacian of it? Using this definition and this formula. This is a formula, very much a formula right here. So I want to do that, and I'm not going to have a y right there. I'm actually going to have a yeah, I'll have a y. I'll keep the y. Why not? Actually, no. You know what? I'm going to have a t right here because I want to stick to this t right here. So what is this? Well, let's start with what we have and what we don't have. Okay. Suppose we have this. So we have this. We don't have that, but we're trying to get there. So the Laplacian of u, well, that's really equal to the Laplacian is the divergence of the gradient of a function u of x, y, which I said that the divergence of a function u of x, y is really equal to the sum of the partials in the corresponding directions. So in this case we have how many independent variables? N equals 2, x and y. So I'm going to say over here that I have the gradient, which actually the gradient of this function would be what? Well, let's see. The gradient operator of the function u would be this. So we would have. So I'm gonna have the sum. I'm gonna write this in. The sum from I equals 1 to n of partial d x I e sub I dot product with the sum I equals 1 to n, because this right here is right here, but I don't have a u on it because this doesn't have a u, so I'm not going to have this u right here on here. The gradient acting on the function u, this is du dxi e sub I, where n is n is equal to 2. So really this is equal to, and in math we usually work down the page, not across. So usually when you're doing like a derivation, you go down. You're doing a proof, you write across. Usually. Now let's look at this. So we have the sum from I goes from 1 to 2 d dx I e sub I, and I should make the small note that x sub 1 will be equal to x and x sub 2 would be equal to t. Okay? Because notice, I am interested in finding what is. Oops, I found a small little carry through error in this. This should be a t right here. Because we're interested, we're interested in the Laplacian of u of xt, which the Laplacian of u of xt is going to give birth to this second order partial differential equation. So we got x, we have x and t, but over here I have x sub i's and e sub i's. So we have to find a way to make these x's and this t become a x, or this x sub 2 become a t and this x sub 1 become an x. So this notation will work. So we have this right here. So this is right here, dot product with I from 1 to 2, summation I goes from 1 to 2 du dxi e sub I, which is equal to, well, let's see, let's take a look at this. This will be the partial with respect to x sub 1 e sub 1 plus partial with respect to x2 e sub 2. That's what the index goes into here and here. It's a 1 1 plus, because the summation, the 2 goes into here and here. Dot product, because this is a vector. Okay, these are like these would be like, if you want to get all with a fancy little hat notation right there. These are vectors in the unit vector directions. Same thing here. We have the 1 goes into here and here, so we have dx 1 u e sub 1 plus du dx2 e sub 2, which is really equal to, remember what a dot product does. Dot product takes and it adds together, it multiplies and it adds together corresponding coefficients of the components of the vector in the same direction. So I'm going to take this and multiply them together. So I get dx1 times du dx1 in the e sub 1 direction, and I'm going to add that to, now I'm going to take this and this, multiply this together in the e2 direction. Dx squared times du dx2 in the e sub 2 direction, which this is the partial derivative with respect to x1. Take the derivative again with respect to x1. I get d squared u dx1 squared e1 plus d squared u dx2 squared e2, which is really equal to, what is this equal to? Let's see. We have what? We have x1's, so we said x1 is x. Okay, but this is u, second partial derivative of u with respect to x1, so I have u x1 x1 plus u of x2 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 x2, which is really equal to what? It's equal to, I said x1 is x, so it's like u of xx plus, and x2 is t, u of tt. So I have here that the Laplacian operator on a function u of two variables is equal to this second order partial differential equation. So now is u xx plus u of t, and we're just going to set it equal to 0 for purposes that I am not aware of yet. Is this equal to 0? Is this linear? So same idea. We were discussing what does it mean for something to be linear. So let's find its operator. The operator that gives us this would be something of this form. L of f would be the second partial derivative with respect to x of some function f plus the second partial derivative of some function with respect to t of some function f. So now consider u plus v and c element of the field. So u plus v and c is a scalar element of the field. So I want to see what L of u plus v does. L of u plus v, well, that's just d squared dx squared of u plus v plus d squared dt squared of u plus v. Well, that's a really ugly u, sorry. So this is equal to, throw this in there, I get u xx plus vxx plus, throw this in there, because we're allowed to distribute. This is u t plus vtt. Rearranging terms, I get uxx plus utt plus vxx plus vtt, which is really equal to L of u plus L of v. So satisfy the first property, and it will ... satisfy the second. That is, I want you to try it at home. L of cu. I want you to determine if that's equal to c of L of u. If it is, then Laplace's equation will be linear. Equation is linear. And it will be. Sorry to spoil it for you. But, okay, I pretty much think I've covered a lot of what I wanted to talk about. However, I want to discuss solutions to Laplace's equation. Let me see. A solution to this equation right here is called a harmonic function. So solutions to Laplace's equation are harmonic functions, and some harmonic functions are used in physics for all sorts of weird things. This isn't a channel about physics. If you want to find that stuff out, go ahead, Google it. But I was able to find that one over the square root of x squared plus y squared plus z squared is a harmonic solution. So I'll call this u of x, y, z. Given some function, I can go ahead and do this. Given Laplace's equation. You know what? This might even work up here. Take this. Of course, we have to switch the variables up a little bit. So let's see, 1 over square root of x squared plus, I don't know, t squared plus z squared. I think this might work. For Laplace's equation. I'm not sure. Go ahead, check it out. If it doesn't, then just mess around with the stuff until you can figure out a way to make it work. The main idea that I wanted to talk about is solutions to Laplace's equation are called harmonic functions. And there's a whole study of these things. I even read a little bit about being weak harmonic, and I don't know, it's kind of interesting. So yep, I hope you enjoyed the video. There's a lot of stuff in here, so you might want to watch it again, see what you can think of. Okay, thank you very much.